Have you ever dropped your keys and just watched them fall? Seems simple, right? But what's really going on there? Well, the physics of falling is actually packed with these amazing, surprising truths that kind of go against our everyday gut feelings. And in this explainer, we're going to dig into all of them.
Okay, let's just dive right in with a classic. This was actually done on the Apollo 15 mission. So picture this. You're on the moon, there's no air, you hold out a heavy hammer and a super light feather, and you drop them at the exact same time. Which one do you think hits the ground first? Have a think about it. We'll get back to the answer in just a bit.
So first things first, before we can even answer that question, we got to get our terms straight. Because the phrase free fall probably doesn't mean what you think it means. It's a lot more than just something heading downwards.
In the world of physics, an object is officially in free fall when the only thing pulling on it is gravity. That's it. So for what we're talking about today, that means we're ignoring air resistance, we're pretending we're in a vacuum, and the object isn't being pushed or held by anything.
And this is where it kind of shatters our common sense. We usually think falling means going down. But in physics, an object you throw up in the air is in free fall the entire time. It's in free fall on its way up, it's in free fall for that split second it stops at the very top, and it's in free fall on its way back down. The whole trip.
So if free fall covers this whole entire journey, what's controlling it? Well, it all boils down to one single, super important number. You could call it gravity's golden rule.
And here it is. Meet G, the acceleration due to gravity. Here on our home turf, Earth, its value is 9.81 meters per second squared. This little number is the absolute star of the show. It's what determines how the speed of any object in free fall is going to change every single second.
But here's a really important little detail. While g is the value, 9.81, acceleration is what we call a vector. It has a direction. And since gravity always pulls things down towards the center of the Earth, we just say that direction is negative. So the acceleration for anything in free fall is always negative 9.81. That minus sign, it's just a physicist's shorthand for downward.
And this right here brings us to the most powerful and honestly, the most mind-bending idea in all of this. As long as we're ignoring air, every single object in free fall has the exact same acceleration. Your keys, a bowling ball, a feather, it does not matter. Their mass is totally, completely irrelevant.
Okay, so let's take that golden rule and apply it. Let's head back to that puzzle we started with and see what happens when we compare falling on Earth to falling on the moon.
See, the pull of gravity isn't the same everywhere. On the moon, g is way smaller, only about 1.62 meters per second squared. That's roughly a sixth of what it is here on Earth. And it's exactly why you see those videos of astronauts taking those huge floaty bounces. Gravity's pull is just a whole lot weaker.
So, back to our hammer and feather on the moon. We know there's no air resistance, and we know mass is irrelevant. So what does that mean? It means both objects, the heavy hammer and the light feather, are going to accelerate downwards at the exact same rate, negative 1.62 meters per second squared. The result? They hit the dusty lunar surface at the exact same time.
Okay, so we've got a handle on things just falling straight down, but what about the more interesting case, when you throw something up into the air? Well, it turns out that journey is just beautifully, perfectly symmetrical.
Let's just imagine a simple scenario. You throw a ball straight up. It flies up, reaches a peak height of 2 meters, and then falls right back down into your hand. Now let's break down the numbers on that little trip. Just look at that perfect symmetry. The ball leaves your hand going up at 6.3 meters per second, and it comes back to your hand coming down at negative 6.3 meters per second. The exact same speed, just in the opposite direction. And the time it takes to go up, 0.64 seconds. The time to fall back down, the exact same. It's like a perfect mirror image.
Now, this beautiful symmetry leads to a classic physics question that really trips people up. Right at the very top of its path, for just a tiny instant, the ball stops moving. Its velocity is zero. So if the velocity is zero, does that mean the acceleration must also be zero?
And the answer is a big, resounding no. Absolutely not. Think about it. Gravity doesn't just switch off for a second because an object stops moving. The acceleration is constant through the entire flight. Gravity is pulling down on the way up, it's pulling down at the top, and it's pulling down on the way back down. It is always negative 9.81. If it were zero at the top, the ball would just float there.
All right, to wrap all this up and really make it stick, let's just blast through the 5 most common mistakes people make with free fall. If you can get these down, you'll be thinking like a physicist in no time.
Okay, here we go. 1. Going up means you're slowing down, so acceleration is negative. 2. To even go up, you have to start with a positive velocity. 3. Throwing something down makes it start faster, sure, but it doesn't change its acceleration. That's still negative 9.81. 4. Remember, at the tippy top of the path, the vertical velocity is always 0. And 5, the big one, acceleration at the top is never 0. It is always, always, always negative 9.81 meters per second squared.
And that brings us to one final puzzle. Now that you've got all this knowledge about freefall, chew on this. Imagine you have 2 bullets. You drop one straight down. At the exact same instant, from the exact same height, you fire the other bullet perfectly horizontally from a gun. Which bullet hits the ground first? The answer might just surprise you.